2 is one-dimensional motion. It's motion along a straight line or in a straight line. It can be like a car picking up speed or moving a certain distance along a straight line. It could be a ball dropped off of a building under the influence of the gravitational pull of the Earth. Those are all one-dimensional motions. But it's not like a football that's thrown a distance up and a distance over. That would be two-dimensional motion, which we'll do in topic 3. So topic 2 is one-dimensional motion. Motion in a straight line. So that's what we'll be focusing on for this unit. We have to model the motion of objects, their position, their change in position, their displacement, their initial speed, their final speed, and acceleration, how fast that speed changed in a system of rates. So let's look at, before we do that, let's make a chart of some quantities that we'll be describing and look at their units and their symbols. Okay, so we'll list first the quantity. Then the units. This is a vector or a scalar. And what is its symbol? Okay, so the first thing that we've already looked at is position. Position of something. The units on that are m, standard units, meters. It's a scalar, and the symbol is just s. The next one is displacement. Displacement also has units of meters, but it's a vector. And its symbol is like that. Now distance, it's also measured in meters, but it's a scalar. And it just has a symbol like that, delta S. Now let's look at time. The next one we'll talk about is time. Instant, at an instant. It has units, S for seconds. It's a scalar. And the symbol for time is T. A time interval, an amount of time, also is measured in seconds, also is a scalar, and it's recorded as delta t. Remember the delta meaning change or an interval for that. How about velocity? Velocity is measured in meters per second, a derived quantity. It is a vector quantity, and it's given the symbol V with an arrow for vector quantity. Speed also measured in meters per second, but it is the scalar version of velocity, and that's just v. Average velocity is also measured in meters per second. It's a vector. And it has a bar over it. And that bar, it has the vector symbol, the arrow, and the bar means average. Average speed. You could guess this one. Meters per second. Scalar. No vector, so just v bar. Acceleration is in meters per second squared. It can be a scalar, there's a scalar version or a vector version. And it could be A or A arrow. Okay? Now, the other thing you see a lot is like change in, or change in position that we have written up there. Could be this is SF minus SI. That's the F means, the subscript F means final position minus the initial position. That gives us our change in position, or our distance, or the vector version from start to would be the displacement. Same for change in speed, VF minus VI, final speed minus the initial speed. So we have to know what we're talking about. Now in one direction, the vector versions are really just plus and minus for that. So now mathematically, we can define some of these values, average velocity and the like, okay? So, math definitions. Well, average velocity can be described, or average speed in this case, can be defined as two different ways. Change in position over, or the position change over the time interval, or it could be the initial velocity plus the final velocity divided by 2. So you have two formulas for that. Okay? Change in speed is final velocity minus initial velocity, and or final speed minus initial speed. And acceleration is our change in speed over change in time. Now, there's vector versions of these as well. For example, you might have velocity is a change in displacement over the change in time interval. And the vector acceleration would be the change in velocity over the time interval. So That's notation. So let's look at an example. Starting from rest, a boy runs 60 meters east in 12 seconds. Find his average speed. And his average velocity. His average scalar acceleration, and his average vector acceleration. Okay, so first thing asked for his average speed. So that was delta S over delta T. We start with our formula. We plug in for our formula 60 meters over 12 seconds. And that gives us 5 meters per second. Now for the vector version of the average speed, it's the same calculation except that we're going east. So we say 50 or 5 meters per second east. So there's his average velocity as well. For his average scalar acceleration, it's change in speed over time. And the change in speed is Vf minus Vi over the time interval. And we ended with if we started from rest, he ended with a speed of what by the time he got to the end? So we need to get this Vf. Well, how can we get Vf? Well, if we remember that we have also this. V bar is not only delta S over delta T, but Vi plus Vf over 2. The initial plus the final divided by 2 like any average. So if our V bar is 5 meters per second and Vi is 0, then we can see that our Vf is 10 meters per second when we bring up the 2. So back over here, we can now finish our problem, which would be 10 meters per second minus 0 meters per second over 12 seconds, or 0.83 meters per second squared. Meters per second over seconds is meters per second squared. And in the vector version of the acceleration, it would be 0.83 meters per second squared east, because that's the one direction it's going in. Okay, so good. Now, for organizational purposes, you're going to get used to something called the RGC, or the really good chart, which we see right here. And this allows you to organize your information to find all the pieces of motion. And the red on it is symbolizing that vector quantities, but for one-dimensional motion, our vector quantities are going to be either plus or minus. So that's not going to be a big deal for finding these values. And we'll use our straight-up math problems for it. So this will help us organize our information. That brings us to the end of 2.1.